and welcome to NPTEL MOOC on Fiber Optic Communication Systems and Techniques course. We will continue in this module what we had started in the previous module, that of analyzing the steps of a single mode fiber, or rather steps of a step index fiber, that is fiber whose refractive index profile was constant inside the core having the value N1, and outside the core, that is in the cladding, which we extend it all the way to infinity on both sides, would essentially have the refractive index N2, which is less than N1. And following our systematic procedure of understanding or deriving the modes of the waveguide or the fiber, we had stopped at a certain point where we had derived the wave equation for the Z component of the electric field. Of course, you could derive a similar equation for the magnetic field as well, and that resulting partial differential equation, because it would couple the r and phi terms in the circular cylindrical coordinate system that we have chosen, the solution was not so straightforward. So, to solve that differential equation, the partial differential equation, we started employing the method called as method of variable separation, or sometimes called as variable separable method. Okay. The essence of variable separable method is to actually write down the unknown solution as the product of functions of individual coordinates. For example, since we know that Ez depends on r and phi, its z dependence is already very well known to us. So, we wrote Ez of r phi as r of r, phi of phi, where r of r is exclusively a function of the small r itself, which is the radius, and phi being the azimuthal angle. Okay, the capital phi of phi is just the function only of this phi, and we substituted this one into the wave equation for Ez, and after simplifying that, we actually derived this particular equation, at which point we had stopped because we did not have sufficient time to discuss the solutions. Now, that is what we are going to do in this module. In this module, we will first understand what this differential equation is, what are the solutions of this differential equation, and once we have the solutions of this differential equation, which is essentially giving us Ez, because Hz also satisfies the equation, which is very similar in this form, except maybe different amplitude constants. So, the form of the solution would remain the same. So, the solution that we are going to discuss now will be applicable both for Ez and Hz, and you know that once Ez and Hz have been obtained, the solutions of Ez and Hz have been obtained, then all the other field components can be readily given by the various combinations of Ez and its derivatives, Hz and its derivatives, right. So, go back to this equation that you are seeing now, and you have to understand that this equation, you will have to write two such equations, one for core and one for cladding, because the refractive index in the core is different from the refractive index in the cladding. Inside the core, n will be equal to n1, outside n will be equal to n2. So, if I were to say I equals 1 corresponds to core, then n1 will be the core refractive index, I equal to 2 corresponds to the cladding, and therefore, n will be equal to n2, and that is why I have written this is k0 square ni square minus beta square. Beta is of course the unknown propagation constant which you are trying to find out. So, now you see this equation, right. I will take another color pen here, okay, and then underline those terms which are functions only of r. So, clearly the terms which I have underlined here with a blue color are functions only of the small coordinate r. Of course, I am assuming that beta is a constant, it does not depend on any other coordinate, and of course, because we have assumed step index profile, the value of n is independent of r and phi, it is just equal to n1 in the core and n2 in the cladding. Now, this term which I am underlining with a different color is a function only of phi. Okay. In arriving at this equation, of course, I have kind of divided everything by r and adjusted the equation such that I get this kind of a functional dependence. Now, let me do something. I am going to rewrite this equation by grouping all the terms which are functions of small r in one side and the functions of phi in the other side, and then what we will get. So, I have r square r double prime by r. Please note that r prime and r double prime denote differentiation with respect to r only. Okay. So, this is the differential that you are actually looking at. So, plus r r prime by r plus k0 square n I square minus beta square times r square plus phi double prime by phi equals 0. Now, I have two functions, right. So, there are three terms which may be collectively combined into one big brace. So, whatever that term that is here in this braces is a function only of r. So, I can change the value of r, I can go from core to cladding, I can do whatever that I want to do with the small coordinate r. Okay. The function or the terms that I have shown in this bracket would represent only functions of that small coordinate r. Similarly, what I would now indicate with another brace is just a function only of phi. You have to understand that r and phi are independent variables. They can change to whatever values that they can change over whatever the limits that they have. Of course, phi is limited to typically from 0 to 2 pi, which covers the one complete revolution around the z axis, okay, whereas r can go from 0 to infinity. At r equal to a, you hit the boundary between core and the cladding, right. But you have a term which is completely function of r, you have a term which is completely function of phi, and for all values of small r and small phi, the sum of these two functions must be equal to 0. The only way that this can happen is when this is separately equal to some integer and this is separately equal to the opposite of the integer, correct. So, only when this phi double prime by phi is equal to some constant, I mean, and I have denoted that constant by nu square minus nu square or nu square plus nu square in case you are looking at the dependence in terms of only function of r. So, what we are saying is that the term which is function only of r is equal to a constant, and the term which is function only of phi is another constant, but this time the constant with a negative sign as that of the other one. The reason because plus nu square minus nu square, the sum of these two will be equal to 0 for all r and phi, and this nu square is called as the separation constant. Okay. That is the reason why we call this method as variable separable method, because we separate the variables by writing the unknown solution as the product of the functions of individual variables, and then when you look at the resulting differential equation, you will actually have terms which are function of only one coordinate, the function of another coordinate. The sum of these two will always be equal to 0, of course that is the original equation condition, and because that has to be 0, these two terms individually must be equal to constants, okay, and further this sign of these constants must be opposite to each other. Okay. So, that is the reason why I have chosen the separation constant to have a minus nu square and plus nu square for the function which I have written as a function of r alone. Okay. Now, there is no reason as to choose this as minus nu square and this as plus nu square, you are free to interchange them, but it turns out that if you choose in the manner that I have indicated, then the solutions can be simplified. Okay. Remember, the goal is not to keep dragged in the mathematics, the goal is to move forward and understand how these functions of r and functions of phi would look like, because your ultimate interest is to find the modes as well as the propagation constant. Okay. So, all the possible modes of the waveguide plus the propagation constant is what you are after. Okay. Anyway, now that I have these two equations individually, I will separate them out and write something like this. I have phi double prime by phi equals minus nu square. Writing it, sometimes my nu does not really look like nu, it may look like v, please excuse that, please remember that this is nu. Okay. So, this is nu square. Okay. So, this equation is essentially a second order differential equation, it is a nice homogeneous equation whose solutions, as you can verify, are given by e to the power plus or minus j nu phi, right. Now, either I can choose e power j nu phi or I can choose e power minus j nu phi, whatever the solution that I choose is perfectly fine. I mean, I can, let us say, choose e to the power plus j nu phi for example. So, this is the solution that I will choose. Okay. And this point that you can actually have solutions which are e to the power plus j nu phi or e to the power minus j nu phi will be exploited later when we discuss something called as linearly polarized modes. There we will see that it is possible to use this e to the power j nu phi and e to the power minus j nu phi in a specific manner to combine and actually make the longitudinal components completely disappear, but that is a story that we will have to wait for another module. Okay. For now I had the option of choosing e power plus or minus j nu phi. I chose e power j nu phi as my solution. Okay. I could, as I told you, equally well have chosen e power minus j nu phi. Of course, you also realize that the solutions could be cosine nu phi and sin nu phi, right, or in general with some additional phase zeta. These are the generalized solutions, but I will not want to go to the cosine and sine form of the solutions because there are little bit of problems with that one. So, dealing with exponentials is much easier. So, I have chosen e to the power j nu phi as the solution. So, that was about phi. What about r? Well, you had this equation, correct, plus r prime by r plus k 0 square n I square minus beta square times r square is now equal to nu square, correct. So, now let me put this nu square to the left hand side and obtain a slightly different equation. Okay. So, I have r square r double prime. I also do something, I will multiply the entire equation by r, so that this r which is in the denominator can be removed and moved to the numerator here. So, I can write this as r and write this as r. Okay. So, please ensure that you understand the manipulation that I am doing. So, now I have r square r double prime plus r prime plus k 0 square n I square minus beta square minus nu square by r square times r square capital R equals 0, and r double prime is basically d square r by d r square and r prime is d capital R by d r. So, this is the equation that I now have, which we need to now solve, right. So, the equation that we now have has to be solved. It is a second order differential equation, all right, but this is a very special equation which has to be solved by what is called as series methods. Okay. Something that you must have studied in your engineering mathematics courses. So, I will not go into the details of this differential equation, but suffice to tell you that this differential equation is an example of Bessel ODE. ODE stands for ordinary differential equation. This is a Bessel ODE of order nu, and because we want solutions which are actually propagating inside the waveguide or inside the fiber, we take this nu to be an integer. Okay. Now, there are different types of Bessel functions. The ones that are actually useful for us will be called as Bessel functions of the first kind and Bessel functions of the second kind of this particular thing. So, these are the different Bessel functions, you must have seen them. So, if this is some j nu of x, this is x, okay, x is the independent variable, the function here will be nu equal to 0, the function here is nu equal to 1, the function here is nu equal to 2 and so on. So, these actually remind you of damped sinusoidal waves. Indeed, for large values of x, you can approximate this j nu of x as cosine x minus nu pi by 2 minus pi by 4 divided by 1 by root x. Okay. So, this can be written for very large values, okay, which means far away from the origin. So, the reason why we call this damped sinusoidal is because they exhibit the oscillatory solutions, and they have these oscillatory solutions are important because that would correspond to standing waves inside the fiber, which is precisely what we started off hoping that we actually get to this type of a solution, because you want standing waves inside the fiber and you want the evanescent or the radiating modes outside the fiber core. Okay. So, this situation is very similar to the slab waveguide situation. In the slab waveguide also you had these standing waves, because these waves were actually getting reflected and therefore creating an interference pattern inside the waveguide, but the interference pattern created in the fiber is slightly more complex than the simple slab waveguide that we have discussed, and that standing waves are actually in the form of, they are not in the form of cosine or sine waves, they are in the form of Bessel functions which look like damped sinusoids, right. So, as x goes to a larger and larger value, the oscillations look more like a cosine wave with some phase shifts give or take, but the amplitude drops because there is a 1 by root x term out there. This 1 by root x is a very peculiar characteristic, or it is not a peculiar, it is a characteristic of assuming cylindrical waveguides, because when electric field goes as 1 by square root r and the magnetic field goes as 1 by square root r, together the product E h, which would be your Poynting vector, I am not writing the vectors, I am just giving you the basic idea, will go as 1 by r, right. So, this is something that we have, the characteristic of a cylindrical waveguide system. Okay. So, this is one type of Bessel function, and this Bessel function will be the solution provided k 0 square n I square minus beta square is greater than 0. Okay. We want this particular term when k 0 square, I need to also include the argument with nu square, right. So, minus nu square by r square is positive. Okay. So, we will have this kind of a solution which is called as Bessel first, or first kind Bessel functions of order nu is the solution provided this k 0 square n I square minus beta square minus nu square by r square is positive quantity. Now, let us introduce two symbols. The symbol that you know earlier, which we called as kappa f, which was the transverse wave number. This time I will call kappa square as k 0 square n 1 square minus beta square. Why? Because beta is bounded by two values. It can at most reach k 0 n 2, at which point the corresponding mode actually reaches a cutoff, okay, and it can go at most up to k 0 n 1, in which case the transverse wave number becomes 0 and beta value will be anywhere in between. Okay. So, these allowed values of beta are discrete, as we have seen earlier, and the transverse wave number can go to a minimum to a maximum, minimum of 0 and to max. So, minimum of 0 at when beta equals k 0 n 1 and a maximum of k 0 square n 1 square minus n 2 square under root when beta reaches k 0 n 2 and gets cut off. Okay. This we have seen earlier in the slab waveguide, exactly same procedure. I am using the same notation as well. In fiber optic literature, it is more common to call this kappa square as u square, okay, but I have avoided that because I want you to constantly remember the significance of this kappa, and of course, since kappa has made its entrance, the next one that to define will be gamma square, which is beta square minus k 0 n 2 square, with the stipulation that gamma square be a positive quantity, which means that beta is greater than or at most equal to k 0 square n 2 square. Okay. So, this gamma is the decay constant, as you have seen, and it would be something that would describe the evanescent field moving away from the core. Okay. So, you have the core, the fields are guided by here, but the field component that is in the cladding would essentially go and radiate away. Okay. And there is another relationship that you must know, which is kappa square plus gamma square is given by k 0 square n 1 minus n 2 square. Okay. This is very important because kappa can go from 0 to kappa max. Okay. When kappa is equal to 0, gamma is at its maximum value, the sum of these two will always be constant, assuming n 1 and n 2 are constant. So, when kappa is 0, gamma is maximum. Okay. So, at this point gamma is maximum and the field essentially decays rapidly outside the cladding. Okay. When gamma is not maximum, it is slower, then the field decay will be much slower. Okay. But when kappa is at its value of 0, the field is decaying outside rapidly, but as kappa rises, the field outside will be decaying much less rapidly. Okay. So, this is something that you have to keep in mind. Okay. Now, this was one Bessel function that we talked about. The other Bessel function that will be the solutions outside the cladding, which you want anyway, is because you are looking at evanescent waves, are called as the Bessel functions of the second kind. Okay. These are the second kind and order nu. Again, the order is nu and I have used k to denote the second kind. Some authors use y, some authors use n. So, these are all different notations. So, please do not worry about those. What is important to note is the shape of these orders, right. They are all exponentials, but they are all exponentials which are actually going towards infinity, okay, and at x equal to 0 and then drop off exponentially. Anyway, this is fine for us, because if you imagine that the solution outside or inside the core is kind of an oscillatory solution, at this point you need to have an exponentially decaying solution which is provided by fitting one of these orders, right. So, if this is my optical fiber core, okay, then the solution would look like this, and outside it has to decay out, right, and these points at which we are going to merge the two solutions, one from the core which is oscillatory and the other one in the cladding which is decaying, are called as boundary matching, okay, and we will have to do a lot of boundary matching here. So, what sort of boundary matching that we need to do? We need to do boundary matching of Ez component, Hz component, E phi component and H phi component. So, you have to match these 4 components, because all these 4 components are tangential component at the boundary r equal to a. Okay. So, these solutions k nu of x also have a asymptotic form, that is, for large values of x they go something like 1 by square root of x. Therefore, at x equal to 0 clearly this is going off to infinity, and then they decay with some constant gamma times x. Okay. This gamma need not be the same gamma, but it could be the same gamma in case you are applying these equations to fiber. Okay. So, you have these 2 type of Bessel functions. Just for record, there are other categories of Bessel functions, some of them go like this. These are clearly not allowed solutions, okay, because they are not going out all right. Okay. So, we have only Bessel functions of first kind of order nu, second kind of order nu as the solutions for Ez. So, now I can write down the solution for Ez in the core as a function of r and phi as j nu, some constant amplitude a. So, a j nu kappa r e to the power minus, or rather plus j nu phi. Okay. Of course, if you want you can also put in e power minus j beta z into this one, it is up to you. And then the solution for H z, because E z and H z satisfy the wave equation of the same nature, the solution will be with a constant b here, same j nu of kappa r e power j nu phi e power minus j beta z, and then you have solutions. So, these are the solutions for r less than or equal to a, meaning these are the solutions for core region of the fiber, whereas the solution for the cladding region will be again some constant c, and instead of j nu which is oscillatory, k nu which is exponential. So, k nu of gamma r, okay, gamma r e power j nu phi e power minus j beta z. For H z the solution will be the same equation, except that the constant instead of c it will be equal to d. So, this is valid for r greater than or equal to a. At r equal to a, you need to match E z, H z, E phi and H phi. To get these expressions for E phi and H phi, you should refer to step 2. For example, E phi is given by minus j beta by kappa square, and then I have 1 by r del E z by del phi. Then I have minus j, or rather plus j omega mu divided by kappa square del H z by del r. Okay. So, clearly if you know both E z and H z, you can use the equation for E phi. Similarly, you can obtain an equation for H phi. These are all coming from step 2. So, I am hoping that you have done that exercise, so that you are not seeing these equations for the first time. You must have been seeing these equations earlier as well because of the exercise that you have solved. So, minus j omega epsilon by kappa square del E z by del r, and then you have minus j beta by kappa square r del H z by del r. Okay. Notice that you are going to differentiate with respect to phi and differentiate with respect to r. When you differentiate it with respect to phi, the assumed solution with respect to phi, you will pull out plus j nu, okay, and when you differentiate with respect to r, you are differentiating Bessel function of the first kind, okay, of order nu, and Bessel function of the second kind of order nu, and these derivatives are not so simple. In fact, there are a set of relations called as recurrence relations which are valid for Bessel functions, which allow you to replace its derivatives in terms of Bessel functions or superpositions of Bessel functions of different orders. Okay. So, I would actually urge you to have a brief look at what these Bessel functions are, go back to your engineering mathematics textbook and then look at the recurrence relationships, look at how Bessel functions are actually solved or Bessel differential equations are solved to really understand what we have done. Okay. Alternatively, you can go to one of your software packages, say MATLAB, and print out a few values of these Bessel functions or few plots of these Bessel functions for different orders and generate pictures from your side, and then look at what happens to these pictures as you change some of the orders or some of the properties or the variable range. Okay. So, I hope that you have done all that or you will do all that, and once you have done that and also derived or made appropriate derivations of del Ez by del phi, del Hz by del r, you will be able to find expressions for E phi and H phi, and these expressions E phi at r equal to a must be continuous in the core and the cladding. Of course, you might ask, what about the equations? Are these equations valid for both core and cladding? Not really. This is for core, and for cladding you replace kappa square by gamma square. Okay. So, for cladding you replace wherever you get kappa by gamma square. Okay. So, please note that these gamma square are not part of these expressions, that is the reason why I am writing them in separate or different color. Okay. So, these gamma square have to be written in place of kappa square. So, when you write the fields in cladding. So, this is the field for cladding, and the black expressions or expressions written in the black color are the expressions for fields in the core. Now, this is an exercise that I am going to leave for you, that is deriving the value of E phi or rather expression for E phi H phi, and then using the expressions Ez Hz, write down the boundary conditions. You will actually get 4 equations. There will be 4 unknowns in your equation A, B, C and D, and you can put all the equations in terms of a matrix. Okay. I will write down the matrix, it is important, but I will not derive the matrix, which I will leave it as an exercise for you. We are going to use this matrix in the next module to actually discuss the solutions. Okay. So, you can see that these matrices are of course with an argument kappa A, because that is the point where you are matching the fields. So, at r equal to a is where you have matched the fields, and these are the expressions that you will get. Okay. So, these are not easy expressions in the sense that they are tedious to write down and then solve, but once in a while if you do it, it would actually be better. So, you have the third row given by this one. So, note the appearance of j nu prime. Let me also simplify these equations by removing the argument of kappa A from everywhere. Okay. It is understood that the argument is either kappa A or gamma A if it is associated with j nu or k nu functions. That is, j nu functions would always be associated with an argument of kappa A, k nu would be associated with an argument of gamma A. So, with that, this is the final equation, or this one you are going to get j mu by k nu prime. The last row is beta nu. Okay. These equations, please verify that you have actually written them down correctly. In the next module, we are going to discuss the solution of these equations and then discuss the properties of modes of the step index optical fibers. Thank you very much.